Learn like a pro.
Today, we're diving into the invisible world of thermal conduction. It's the reason a pan gets screaming hot on a stove, but also why a blanket keeps you nice and warm. We're going to break down exactly how this works, starting with a simple little mystery that I guarantee you've experienced before. Okay, so picture this. You've got a hot cup of tea, you put a metal spoon in it, and just a few moments later, the handle is way too hot to touch, right? But the ceramic mug itself? The handle is perfectly fine. They're both touching the same hot liquid, so what gives? Why is there such a huge difference? Well, that's the exact question we're going to answer. So, to solve this puzzle, we first have to understand the single most important rule in the entire world of heat. You can think of it like a prime directive, one that the universe never, ever breaks. And that rule is really simple. Energy is a one-way street. It always, and I mean always, flows from a hotter place to a colder place, no exceptions. So in our mug example, the energy from the hot tea starts flowing into the colder spoon. And this process is relentless. It's got one specific goal in mind. And that goal? It's called thermal equilibrium. The easiest way to think about it is like a perfectly balanced scale. Energy is just going to keep moving from the hot thing to the cold thing until both of them reach the exact same temperature. And once they're balanced, that's it. The net transfer of energy just stops. The whole system is at peace. So, we know that energy moves from hot to cold to find balance. But how does it actually travel through a solid object, like that metal spoon? Well, for that, we need to zoom in. I mean, way, way in, all the way down to the atomic level. You see, inside a solid, all the atoms are locked into this really tight structure. They can't just wander around, but they can vibrate right where they are. So when you heat up one end, you're giving those first atoms this huge jolt of energy, and they start vibrating like crazy. And these vibrating atoms, they bump into their neighbors, which makes them start vibrating. And then they bump into their neighbors. You see where this is going? It's a chain reaction. It's like a line of atomic dominoes, passing energy right down the line. Okay, but hold on. If all solids transfer heat with this domino effect, why was the metal spoon so much faster than the ceramic mug? This right here is where we find the critical difference between materials that are like an express lane for heat and others that are more like a roadblock. And this comparison pretty much shows us everything we need to know. On the left, in materials like ceramic or wood, you've only got that slow particle-to-particle domino effect. But on the right, you see the secret weapon of metals, free electrons. These little guys aren't locked in place. When they get a jolt of energy at the hot end, they literally just zip straight to the cold end, completely bypassing that slow domino chain. This is the express lane for heat. And this table just lays it all out for us nice and neat. Metals? They use both the vibration and that free electron express lane, which makes them amazing conductors. Non-metals, though, they're stuck with just the slow vibrations, so they're pretty good insulators. And then you have fluids, like air. They're the ultimate insulators because their particles are so spread out that bumping into each other is pretty rare. So here's the really cool part. Once we understand these atomic rules, we can actually engineer things to either move heat super fast or to block it almost completely. And this isn't just some abstract theory. It is all around us, every single day. Remember how we said air is a terrible conductor? Well, we use that to our advantage all the time. A double-glazed window, or the double skin design of a cooler, works by trapping a layer of air. That trapped air acts like a powerful thermal blockade, making it really hard for heat to get through. It's such a simple but brilliant way to create insulation. Okay, so to wrap this all up, let's look at one final, super fascinating case where our own senses can get completely fooled by these exact same principles of conduction. You definitely know this feeling. You're in a room, everything in it is the exact same temperature. But when you step off a warm rug and onto a tile floor with your bare feet, that tile feels shockingly cold. But is it actually colder? And the answer is no, it's not colder at all. The tile and the rug are at the exact same room temperature. The difference is all about conductivity. Tile is a way better conductor than fabric. So when your warm foot touches it, the tile just yanks the heat away from your skin incredibly fast. And here's the thing, your brain doesn't really feel temperature. It feels the rate of heat loss. That super fast heat loss, your brain interprets that sensation as cold. It's a sensory illusion, and it's explained entirely by conduction. So the next time you touch something that feels way colder or hotter than you expect, just ask yourself, is this really about temperature Or is it about conduction? Think about a metal park bench versus a wooden one on a cool day. Once you understand these rules of thermal transfer, you really do start to see them working everywhere.